Hi, today I'm going to talk about NLTS Hamiltonians and Strongly-Explicit SoS lower bounds from low-rate quantum LDPC codes. And this is joint work with Tali Kaufman. So to begin, I'll give a quick review of quantum LDPC codes. Now, the basic idea in quantum error correction is that we start with a length k message of logical qubits, so k qubits, that we will then encode into a larger n qubit physical code state, such that if a corruption occurs on a small number, say at most d, these physical code qubits, we can perform some stabilizer measurements in order to recover the original message. And specifically, the LDPC property, which stands for low density parity check, means that these stabilizer measurements are low weight. So maybe we'll measure this Pauli product of this tensor product of 3 Pauli x's here, this tensor product of 3 Pauli x's here, maybe some tensor products of Pauli z's, another tensor product of Pauli z's, and by measuring more of this type of stabilizer, we are able to then apply some correction and recover the original message. So this paradigm of quantum LDPC codes are extremely useful for error correction due to the basic protocol we just saw. And as a result, there's been a lot of attention given to studying quantum LDPC codes, which accumulated in this breakthrough work, which constructed asymptotically good quantum LDPC codes, first by Panalev and Kalichev in 2022, and then with some follow-up works that gave modified, maybe simpler versions of their construction. And what I mean by asymptotically good here is that these codes have constant rate R, which is the ratio of the number of message qubits to physical qubits. So there's only a constant factor overhead in the additional space we need to encode the message qubits. Constant relative distance. So these codes can withstand an error rate that corrupts a constant fraction of the physical qubits, and constant locality L. So each stabilizer measurement only touches a constant number of qubits in the code. Now, as I mentioned, the construction of these codes was a major breakthrough for error correction. Interestingly, it also led to breakthroughs for complexity theory, which was maybe a bit surprising, maybe not given the prevalence of error correction in classical complexity theory. But many of you probably can see where this is going. There was this breakthrough result on NLTS Hamiltonians from good quantum codes, from these asymptotically good quantum LDPC codes. Anshu, Breukman, and Nurki constructed NLTS Hamiltonians, which I'll define later, but their existence was a big open question in quantum complexity theory. And even before that, there was another breakthrough in complexity theory, this time in classical complexity theory, in which Hopkins and Lin gave the first explicit lower bounds against a linear number of levels of the sum of squares semi-definite programming hierarchy. And specifically against the ability of this hierarchy to solve a certain approximation problem, a certain optimization problem. So in our work, we give, albeit maybe modest improvements to both of these results. So we give strongly explicit lower bounds against a linear number of levels of the SoS hierarchy. So the Hopkins-Lin result turned out to only be weakly explicit in a certain technical sense. Essentially, you need to do some sort of polynomial time Gaussian elimination to actually compute these hard instances that they constructed. So in a very technical sense, their construction doesn't let you just explicitly write down a hard instance. And we kind of remedied this shortcoming. And on the NLTS side, we relax the requirement from having good quantum codes with constant rate, distance, and locality to just having codes with constant relative distance and locality. So we essentially remove the constant rate requirement and in fact show that any positive dimension suffices. We don't need anything close to linear dimension for these codes in order to get NLTS. Now, along the way, we actually introduced some additional codes that may be of independent interest. In particular, we give a new construction of what we call planted quantum LDPC codes. So these are quantum LDPC codes of linear distance and that have guaranteed positive dimension without resorting to parity check counting. So what I mean by this is that if we view a quantum LDPC code like this, where in the middle we have n qubits, and then we have our x stabilizers on the left and the z stabilizers on the right, it's always true that the code dimension, or the number of logical qubits the code encodes, is at least the number of physical qubits n minus the number of stabilizers. This bound I refer to as parity check counting. It's what's been used to show linear dimension for all the previous asymptotically good quantum LDPC constructions. We show that we can actually guarantee positive dimension a different way. We can essentially plant a single non-trivial logical code word in the code and just guarantee that the dimension of the code is at least 1, regardless of how many x or z stabilizers there are. So I'll describe later why this could be interesting for a couple different reasons, and we actually give kind of a concrete application of this to SoS lower bounds. But for now, you can see the motivation is just a new way of guaranteeing positive dimension in these codes. So I'll now talk more about our NLTS result. The motivation for this result comes from the study of hard local Hamiltonians. So if we view local Hamiltonians as a mountain, where the hardness of, say, computing or approximating the ground state or the ground energy increases as we go up the mountain, then somewhere not at the top of this picture, closer to the bottom, maybe in the middle, lies NLTS Hamiltonians. So these are local Hamiltonians in which you need superconstant circuit depth to construct any low energy state. Meanwhile, closer to the top of this mountain are quantum PCP Hamiltonians. These are local Hamiltonians for which it's QMA hard to even compute a constant factor approximation of the ground energy. So not even constructing ground state, just estimating the ground energy. And naturally, we should expect implications to point down this mountain. And indeed, as we should expect, because QMA hardness is harder than just kind of super constant circuit depth, we indeed have that, assuming the well-believed conjecture that QMA is not equal to NP, all quantum PCP Hamiltonians are NLTS. So quantum PCP Hamiltonians are, in a very technical sense, strictly harder than NLTS Hamiltonians, or at least as hard as NLTS Hamiltonians. Now, the first known construction of NLTS Hamiltonians was given by the breakthrough result of Anshu, Breukman, and Nurki in 2022. And this marked important progress, some of the most significant progress we have so far, of getting towards the larger goal of quantum PCP Hamiltonians. In this work, we don't really go up the mountain, but rather we go sideways. So we give more constructions of NLTS Hamiltonians. Or in other words, specifically, we relax the conditions on a code under which that code yields an NLTS Hamiltonian. But I guess this can still be viewed as kind of progress upwards, in the sense that the more constructions we have down here, the more constructions we have NLTS Hamiltonians, the more opportunities we have and flexibility we have for finding construction that will generalize to something maybe higher up the mountain. So that's kind of the motivation for our work. Great, so I should now formally define what is an NLTS, or a no low energy trivial states local Hamiltonian family. This is a family of local Hamiltonians normalized between 0 and the identity, along with some positive constant epsilon, such that as n goes to infinity, the circuit depth needed to construct an epsilon low energy state for these Hamiltonians approaches infinity. So no constant depth circuits can construct epsilon low energy states for all local Hamiltonians in the family. Great, so how are we going to prove the circuit lower bounds that we need to obtain NLTS Hamiltonians? Well, Elder and Harrow and the subsequent work by Anshu, Borkman, and Nurki took the approach that we can actually use this idea called well spreadness to establish circuit lower bounds. So say we imagine measuring a state rho in the computational z basis. So we get out a bit string, a length n bit string, and this rectangle here represents the set of all length n bit strings, or f2 to the n. And furthermore, let's suppose that we have a set here and another set here, both shown in red, such that there's a constant probability that our measurement lies inside each of these two sets. And let's suppose that these two sets are linearly far apart. They're separated by a Hamming distance that's linear in n. If this is the case for our state rho, if it has these two far apart sets, each with a constant probability of our z basis measurement landing inside the set, we say that rho is well spread. And it turns out that if rho is well spread in this sense, we're guaranteed that every circuit constructing rho has at least order log n depth. So there's no constant depth circuit constructing rho. So this is great. Now to show an LTS, all we need to do is find a family of local Hamiltonians such that all the low energy states are well spread. Now it turns out that, again, following the work of Elder, Harrow, and Anshu, Borkman, and Nurki, quantum LDPC code Hamiltonians are perfectly suited for this task. So now at this point, I'm going to give kind of a brief crash course with a bit more background on quantum LDPC codes to specifically define what is a quantum LDPC code Hamiltonian. So this picture I flashed up before. So to elaborate on it, we represent the code qubits by these boxes in the middle, these black boxes. Each box on the left, each green box, represents an X stabilizer, and each orange box on the right represents a Z stabilizer. For instance, this X stabilizer corresponds to the product of the Pauli X's on the four code qubits incident to the highlighted box on the left. So each X stabilizer is a tensor product of 4 Pauli X's. Each Z stabilizer is similarly a tensor product of the 4 Pauli Z's incident to the highlighted box on the right. And in this case, we can see that the X stabilizer and the Z stabilizer intersect on exactly 2 components. And this means that these two Paulis, the product of the Pauli X's and the product of the Pauli Z's, commute. And indeed, for a CSS or a stabilizer code, the one condition we need on the stabilizers is that all the stabilizers commute. Great, so as I mentioned before, the dimension, or the number of logical qubits in the code, is at least the number of physical qubits n minus the number of stabilizers. And we formally define a logical operator to be any Pauli operator that commutes with all the stabilizers, but is not itself a stabilizer. So for instance, the tensor product of these two Pauli Z's, we can check that it commutes with all the stabilizers, but is itself not a stabilizer. So it's a weight 2 logical operator, and thus the distance of the code, which is the minimum weight of any logical operator, is in this case 2. Finally, the locality is simply the maximum weight of any stabilizer. Now we can define the code Hamiltonian to be the average of an X and Z code Hamiltonian, where each of the X and Z Hamiltonians consists of essentially an average over all of the respective X and Z stabilizers of the identity minus that stabilizer divided by 2. Intuitively, H sub X here is a Hamiltonian that intuitively counts the number of X stabilizers that are violated, while HZ counts the number of Z stabilizers that are violated. And so overall, H counts the fraction of total stabilizers that is violated. For instance, if we take the energy with respect to the code Hamiltonian H of a true code state, we'll get energy 0. So the ground space of H is the code space. And if we take the energy of a state that violates all the stabilizers, so something that's very far from a code state, we'll get energy 1. So the code Hamiltonian is really just measuring how many stabilizers are violated. So now we can start getting to some actual NLTS statements. So Elder-Harrow in 2017 showed that a quantum LDPC code Hamiltonian is NLTS if the code exhibits linear distance, any positive dimension, and a very strong property called local testability. But unfortunately, this local testability property is quite strong, and we still don't know how to obtain linear distance codes with this property. So the Elder-Harrow construction was just conjectural. And I guess, of course, they proved this following the basic outline I showed before by showing that codes satisfying these properties have code Hamiltonians such that all the low energy states for this Hamiltonian are well spread in either the X or Z basis. Now, Onchu, Broikman, and Nerke went from this conjectural construction to a concrete explicit construction by showing that quantum LDPC codes with linear distance, linear dimension, and a weaker testability property, which I'll call clustering here, yield NLTS Hamiltonians. And essentially all the previously known asymptotically good quantum LDPC constructions satisfied these three properties. However, I will note here that this linear dimension requirement of the ABN paper is stronger than the positive dimension requirement of the Elder-Harrow paper. So in our work, we kind of get the best of both worlds. We show that LDPC codes with linear distance, any positive dimension, and this weaker clustering property yield NLTS code Hamiltonians. And as I mentioned at the start, we also give this construction of planum quantum LDPC codes, which possess these three properties but may not, likely do not have linear dimension. So in this respect, we give kind of additional constructions of code Hamiltonians that yield, I guess, slightly new NLTS Hamiltonians. I don't have time to give our whole proof, so I'll just highlight the key point in the proof, which is the use of an uncertainty principle. So say we imagine measuring a state rho in both bases, the X and the Z basis, where each box represents the set of all length n bit strings corresponding to the set of all possible measurement outcomes in the respective bases. And let's say that there's a set S, some chosen set S in the X basis, and some chosen set T in the Z basis. Now, an uncertainty principle says that we cannot find S and T such that there's a very high probability, like probability 0.99, that measuring rho in the X basis gives an outcome in S, and measuring rho in the Z basis gives an outcome in T, as long as some property of S and T are satisfied. So for instance, Elder and Harrow used the property that if S and T are eigenspaces of respective anti-commuting logical operators, X bar and Z bar, then essentially we cannot find sets S and T such that rho has a high probability of landing in either one when we measure in the X or Z basis respectively. Meanwhile, Onchu, Broikman, and Nerke used a different uncertainty principle in their result. They simply use the fact that if S and T are sufficiently small, so if the product of their size is much less than 2 to the n, then again we cannot have a very high probability of rho landing in each of these sets when we measure in the respective bases. And I guess the point is both these results use this uncertainty principle to show well spreadness in either the X or Z basis. Now, Elder and Harrow established this condition. They found these sets, appropriate sets S and T that are eigenspaces of these logical operators, using the local testability of the quantum code. Basically, they use the fact that in locally testable quantum codes, the low energy states correspond almost exactly to, or they correspond very closely to true ground states, to true code states. And because of that, they could kind of use these logical operators on the low energy states. Meanwhile, Anshubrook-McNerney had this weaker testability notion of clustering, and so they kind of combined it with linear dimension to find sets S and T that were sufficiently small. They really used the linear dimension to show that S and T were sufficiently small to satisfy this inequality, and then they applied the uncertainty principle to get will spreadness in one of the two bases. So in our work, we essentially showed that the Elder-Harrow, the uncertainty principle that Elder-Harrow use can actually be applied to codes satisfying this clustering property without linear dimension. And this is how we kind of relax the linear dimension requirement to just having linear distance quantum LDPC codes of any positive dimension. And the key idea behind our work in getting this relaxation is that while the clustering property is weaker than local testability, it creates kind of additional clusters, additional low energy states that do not correspond to any true code state, unlike locally testable codes. But like locally testable codes, we can still apply logical operators to all of the low energy states. The low energy states still respect the action of the logical operators, even if these low energy states don't correspond to true code states. And because of that, we're still able to use the Elder-Harrow uncertainty principle and I guess obtain the stronger result that linear dimension is not necessary for quantum LDPC codes with clustering in order to get NLTS Hamiltonians. Great, so I've just told you how we can do some work and show that linear distance quantum LDPC codes without linear dimension yield NLTS Hamiltonians. Do we even have any constructions of these? Because as I may have mentioned before, all the previously known linear distance QLDPC code constructions, in fact, just naturally had linear dimension because they went through this parity check counting argument. It turns out that we can construct such low dimensional codes, at least probably. We construct codes which we can only lower bound the dimension by 1. We don't know how to upper bound the dimension, but these codes seem to intrinsically, kind of by design, have low weight, have low dimension. And in any case, we'll see a specific application of this construction, regardless of what their true dimension is. So I don't have time to give the full quantum construction of these codes, so instead I'll give the classical intuition, and that will at least be suggestive of what the quantum construction is. And the classical intuition for these planed codes, or these planned, I guess, classical Tanner codes, is that if we take an expander graph and fix some constant size inner code C sub n, then classically we can get a Tanner code C whose code words are labelings of edges with bits. So every edge is assigned a bit in the code, that's 0 or 1. And the constraints are simply that the local view of every vertex, so the bits on the edges that a given vertex sees, must form a code word in the inner code. So for instance, this highlighted vertex in the top right sees 1, 1, 0 on its edges. So if this assignment lies in the code, then 1, 1, 0 must lie in the inner code. So that's a classical Tanner code. Now, how do we ensure positive dimension in a classical Tanner code? Well, the standard method is to simply count the number of linear constraints. We can count the number of variables or the number of edges, count the number of constraints because we have however many constraints the inner code has times the number of vertices, subtract them, and if there's more variables and constraints, then we have positive dimension. But we can alternatively use a planting method. We could instead simply require that the all ones vector, like 1, 1, 1, lies in the inner code, and then we are guaranteed that the all ones vector lies in the final classical Tanner code, simply because then every vertex will see only ones, which is an inner code word. And when we combine this with the fact that all zeros is also in the inner code and in the entire classical Tanner code, we get at least one non-trivial code word. So we get code dimension at least one, regardless of how many constraints there are in the inner code or in the global code. So our contribution here is to introduce a quantum analog of this planning technique. The classical technique seems very simple as it is. It's almost like a complicated way of producing repetition code. The classical construction turns out to be a little more complicated for reasons that I don't have time to get into here. But ultimately, we do obtain such planted quantum Tanner codes with linear distance and with dimension at least one. Now, where are these planted codes useful? I've just told you how you can take a perfectly good linear distance quantum LDPC code and reduce the dimension, whereas typically we'd think that higher dimension is a better thing. In one kind of, I guess, high level, almost philosophical viewpoint, this is kind of a different technique for avoiding parity check counting and bounding the dimensions of our codes. And this type of thing there's been questions in the classical coding theory literature on how we can avoid parity check counting. So maybe this technique could be useful somewhere else in the future. But more concretely, we obtain this result I mentioned earlier of strongly explicit lower bounds against a linear number of rounds of the sum of squares semi-definite programming hierarchy. In particular, we obtain the first such strongly explicit lower bounds for the problem of obtaining a constant factor approximation to a CSP, to an optimization problem. So in brief, what are SoS lower bounds? Well, the sum of squares hierarchy is a powerful classical algorithmic framework, so it's important to note that now I'm talking about classical algorithms, not quantum algorithms. But we're going to use quantum algorithms to produce lower bounds for this we're going to use quantum codes to produce lower bounds for this classical algorithmic framework. And because SOS seems to be so powerful, we really want to understand its limitations. We want to understand lower bounds are hard instances of problems that SOS cannot solve. And it turns out that basically all the known hard instances are the SOS lower bounds for this problem of computing a constant factor approximation to, say, some CSP were random until this paper of Hopkins and Lin, which constructed the first explicit SOS lower bounds for this problem. I guess specifically the CSP they looked at was kind of max 3 XOR, but I guess this precise CSP isn't too important here. And the major downside with this result is that it was only weakly explicit. Their construction of hard instances for SOS was based on good quantum LDPC codes, but it needed Gaussian elimination to find an explicit non-trivial code word in the QLDPC code. And this runs in polynomial time, so it means that kind of for a given n, their algorithm couldn't give like a polylog time algorithm to output a given part of this instance. It really needed to do like a long polynomial time calculation to construct this code word. And so in a very formal sense, it was not strongly explicit. And we resolve this problem by simply just applying our planted quantum Tanner codes, because these always contain the all ones code word. So we don't have to do any Gaussian elimination to find a non-trivial code word. We know that the all ones code word is a non-trivial logical code word in these codes. So just to summarize, we construct, I guess our 3 main contributions are NLTS Hamiltonians from low-rate quantum LDPC codes, planted quantum LDPC codes, and strongly explicit SOS lower bounds. So thank you.